Okay, so thank you everyone for joining us today and welcome to the AI seat on what's probably one of the hottest topics in AI today, reinforcement learning. It's always been a big deal, but since GPT 3.5, remember that in prehistory, when it burst into our lives as a result of RLHF 2 years ago, it's been garnering more attention than ever. There are even jokes, by the way, running around the internet about reinforcement learning. And I wanted to tell you one of them, but I'm not sure it's very rewarding. Oh, very good. Yes, I was concerned. Okay, yes, okay, you got it. Okay, you're the right kind of people. Great. Okay, next joke is about Star Wars. Okay, now we know who. Jesus Christ. Okay, bad behavior. Okay, so I apologize for everything and to everyone. For those of you who weren't here in the last session, my name is Roy Tsazana, and I'm a futurist and a researcher at the Blavatnik Center for Cyber Research here in Tel Aviv University. And it's my pleasure and honor to host this session about reinforcement learning with some of the top experts in the field. We know they're the top experts in the field because they are sitting at the front row right here. They're going to share their advances and insights with us today. So without further ado, let us begin. I would like to invite to the stage Professor Yishay Mansour. Wait a second, Yishay. I wanted to present you as, you know, with all the respect that you deserve. So Professor Yishay Mansour is a professor at the Blavatnik School of Computer Science here in Tel Aviv University, and he's also a researcher in Google Research Labs in Israel. He will speak with us today about delay and cooperation in reinforcement learning. So I'm sorry to have delayed you, and please come aboard, cooperate with us, and tell us all about that. Thank you.
Okay, I'm delighted to be here and sort of to talk about reinforcement learning. So I'll sort of talk about delay and cooperation, but since it's sort of the first talk of the session of reinforcement learning, I'll sort of try to give also a slight biased overview of how I see the field. So reinforcement learning is not a new field by any means. It sort of dates back probably to the middle of the 20th century. It has roots on the one hand side in engineering, in computer science and operation research. On the other hand side, it has to do with studies of humans and animals in psychology, in economics, and in neuroscience. My research is, of course, through the lens of computer science and algorithms, but this is sort of what is reinforcement learning about. And as Roy mentioned, reinforcement learning had many success stories. I think most of the success stories up to very recently have been in playing games, either playing sort of backgammon, this is dating back even to the 1980s, and then playing chess, Go, and I think, so from my perspective, I think the main breakthrough in the recent trend of reinforcement learning was the DeepMind view of playing Atari games. And the goal, I think, in all those games was not to build a good player. This is important to understand. Cesar, when he designed his backgammon, did not try to sort of get a good player, but the main goal was to demonstrate that you can learn with minimal additional information from the outside. I think in all those challenges, the real challenge was to get a minimal amount of information. In the Atari game, what DeepMind did is that essentially the system that is playing doesn't get any real information, it just gets the screen as it is and plays. Of course, the main challenge of that haunts reinforcement learning is controlling robots. This is where we want to go. This is usually our theme, and we have, let's put it, mediocre success so far. But there are surprises, and the recent surprise is sort of the trend of the LLMs, the large language models, which in some sense, beyond using deep neural nets, it is using methodologies that have been developed in reinforcement learning in order to both fine-tune them and mainly reinforce using human feedbacks and and optimize those systems. Okay, what am I going to talk about today? So today I'm going to basically talk about things that we do in our labs. The perspective that we are going to look at is from a theory point of view. Essentially, I would like sort of to look at both of reinforcement learning and online learning from this perspective. And the main two themes that I would like to mention to you today and sort of to overview is both delay and cooperation as it is related in reinforcement learning. Okay. So why do we need delay or cooperation? So I think in many applications, delay is very natural, sort of. When you make a decision, it takes time to see the outcome. I think the most obvious thing is sort of clinical trials. And clinical trials are sort of have been at the birth, I think, of reinforcement learning, and the basic models of multi-arm bandit in the 1950s were invented in order to answer the question, how can we evaluate clinical trials and how can we minimize the amount of exploration that is required? Another sort of newer trend is online advertisement. So assuming that all of you probably saw an online advertisement when they visited some website, essentially what really happens is that although sometimes the advertiser would pay for a click, the real outcome is coming down the stream when the buyer is doing other action and eventually purchases. So there is an inherent delay between the action that is performed and the outcome that is viewed. And finally, even in the recommendation system, when we recommend to a user either a movie, a song, an article, usually there is a substantial delay between the time of recommendation and sort of the time where the user reacts, and not only reacts by clicking, let's say, and seeing the video, but giving us enough information that we will be able to determine whether he liked the video or didn't like it, and other things. So this is all has to do with delay. Another topic that I would like to mention, which is, I think, very related, is essentially cooperation. So the cooperation would be cooperation having multiple users or multiple agents in the environment and having them interact with one another. So in all those applications, you can see that there are multiple agents, and essentially we would like to transfer the information from one set of users to a different set of users, or in other words, we would like to see how much can we benefit by having the learning spread across multiple agents. Okay, so this was sort of the high level. There isn't going to be a lot of math in this talk, but this is sort of like the 2-3 slides that I allowed myself to slightly dive in. Okay. So what I would like to sort of explain is sort of what is online learning as a discipline inside machine learning, and then I'll sort of explain how is it related to the reinforcement learning and the basic results. So in online learning, we have an agent that continuously needs to select actions. So it needs to select an action at time t, it selects an action at, and then it observes a loss for the action that it selected. And the losses could be either stochastic, so there is some distribution given the action that decides the loss, or they can be adversarial. And adversarial is sort of, for those of you who are not familiar, it sounds very strange, sort of. Loss are adversarial, then I can just give no reward. There is two reasons why to think about adversarial. We are going to set the benchmark. Okay. The reason why we would like to look at adversarial is because we would like, in some sense, to minimize the set of assumptions that we have about the rewards. We will set the benchmark in such a way that it would make sense. So when we talk, especially when we talk about adversarial rewards, but also about stochastic, what we would like to see is how different, how much are we losing by not knowing the model. So the agent goal is minimize its losses over the t time step. And really, the main agenda of regret minimization is trying to capture how much are we losing but not knowing the model. Okay, so regret minimization, what we really measure is not the absolute losses, and which depends on the structure of losses. Rather, what we would like is to compare our online algorithm to an optimal policy and asking how much worse are we doing compared to the optimal policy. So this would be our regret. So our regret is really going to be relative compared to the optimal policy. So if the optimal policy is doing very badly, we are allowed to do badly. If it's doing great, we should be also doing great. And the goal is that sort of as time progresses, on average, our losses should approach the losses of the optimal policy. Or in other words, if we look at the difference between the losses of the online versus the losses of the optimal policy, we'd like this difference on average to be vanishing. Okay, so what is the optimal policy in some sense? So the optimal policy in the problem in the online learning, if it's stochastic, then there is a single best action. So we would like to compare ourselves to knowing the best action while we don't know it in advance. In the adversarial setting, inspired by the stochastic setting, we'll still want to compare to the best action, or more generally, we'll have a set of policies and we'd like to compare ourselves to the best one of those policies. So let me sort of give you it very briefly how can we sort of solve those questions and what goes into those algorithms and results. So the agent assumes that for beginning we have full information. What is full information? The agent observes the losses of all the actions. Every time it does an action, but knows the losses of any other alternative action that it might have done. So then we have sort of a bunch of algorithms that essentially what they are doing is trying to sort of follow the best alternative, but following the best alternative is not the right methodology. But if we add some noise to the best thing, like doing a soft max, this will give us sort of the results in this slide. So formally, sort of for each action, we can see how much loss it accumulated until now, and then select the action with a probability distribution which is exponential in those losses. So things that have a small loss would have a high probability, things that get a high loss would get a very small probability. And now we would like to look at what is the online loss, right? So how much in expectation is the online losing? And here is sort of a rather surprising result. We can compare the online loss to the loss of the best action in hindsight, even for the adversarial setting. And while both the loss of the online and the loss of the best action would very naturally will grow linearly with the time, their difference will grow only something like square root of t. So on average, it's sublinear. So on average, it will be vanishing. Okay? The next is sort of looking at online learning with bandit information. So here we have only the information that the action that we indeed perform. And the main challenge here is how do we sort of do the counterfactual? How can we give an estimate for actions that we didn't observe? So of course we cannot give an estimate for actions we cannot observe, but we can build unbiased estimators. So the main thing here is that we build unbiased estimators for the actions that we did, that on average, in expectation, they are unbiased. And the main challenge is to bound the variance of our estimators. And again, the results conceptually would be very similar. The online learning is performing like the best action with some additional regret, which is sublinear. Okay. This is what I have to say about online learning. And I want now to connect it sort of to cooperation and delay. Okay. So in cooperation, I would like to think of having multiple agents make decisions. So they have identical goal, they are willing to share the information, and their main goal is to minimize their overall regret, either individual or average regret. And the research is trying to ask, how much can we gain through cooperation? Because of course, each agent can work in isolation, minimize the regret. The previous two slides says it will get a sublinear regret in any case. The main question is, how much can we gain more? This is sort of a sequence of work that I think I've mentioned the first two, that can show that we can sort of substantially, in some cases, gain from cooperation. The other thing is sort of delay. So delay, as I mentioned before, in many reasonable cases, we do observe the feedback in delay, either due to sort of the inherent thing in, let's say, online ads, recommendation, or clinical trial. But if we think about it, when we have cooperation, it's another reason why we do have delay, because it will take time to forward the things and the information from one agent to another. Okay. So let me sort of start with sort of talking about cooperation in multi-arm bandits. So in this case, we have sort of N agent and T time steps. And the benchmark, we should think about two benchmarks. We can either let one user run all the time, so we'll allow him N times T time steps, or we can think about the full information. Right? So those two things we will not be able to beat. How close can we get to them? So we can run sort of off-the-shelf algorithm for multi-arm bandit, like the one that I very briefly mentioned. And the basic idea is, where do we gain? So initially, those algorithms use a uniform distribution. So essentially, they are getting almost a full feedback. Eventually, when they concentrate on a single action, what will really happen is that the rare event of exploration would be multiplied by the number of agents. And essentially, we can use this in order to get an improved bounds. So you can see as the number of agents would grow, this would sort of disappear, and we'll have a sort of only a square root t, independent from the number of actions. Now, an added value is looking at communication graphs and then there is an added layer that we need to communicate between the agents. So in this work, we sort of looked at the properties of a graph and identified the independence number as the main property, and using it, so alpha g is the independence number of the graph, and using it, we sort of were able to control the average regret. In a later work, we were sort of looking at more individual regret, and we were able sort of to get the regret as a function of the degree of each node. And the algorithm here, while not being symmetric, sort of split the agents into clusters, and in each cluster it sort of defined an agent that would lead the cluster, and using it, so making sure that the cluster have a small diameter and high degree for the leader, was able to derive the individual regret. Okay, so one exciting work that we sort of have in progress under submission now is in cooperation in stochastic multi-arm bandits. So I'm getting a 2 minutes warning. I'll do this slide and then finish to the conclusion. Okay, so So basically, in stochastic multi-arm bandits, we can get regret of this type, right? And the delta is sort of the suboptimality. And the thing that I like here is that just think of a graph that is connected, just a line graph. So you think, okay, when you do the communication, every node is fairly far from each node. So how much can we benefit when you have such a low connectivity? The surprising result is that we can get rid of the suboptimality gap and get a bound which is independent from it. Here is the intuition. In order to eliminate an action, we need 1 over delta squared samples. Each one of them gets a delta regret. So when we multiply them, we get a regular bound. But when we have a line, when we look on how much information are we gathering, it will grow quadratically. So after 1 over delta time steps, we'll have 1 over delta squared information, which will give us a constant regret. Okay. So I'll have to delay the delay and probably not do it this time. But let me sort of finish with a few words about future work. So for delay, I think we have near optimal bounds and a good understanding. But I think but this is for the vanilla delay. I think other sort of structured delays are interesting, especially when the delays do depend on the rewards. So sort of, in some sense, if you think about in the ads, there's a different delay in order to understand that someone doesn't click versus someone clicks. So the delay does depend on the outcome. For cooperation, I think there's much more to do. Sort of what we did was sort of missing the issues of incentives. This is one thing that is definitely interesting. And when we have multiple agents also, it would be interesting to understand what happens when the agents are similar but not identical. And let me end with this note.
Thank you, Professor Mansour. Are there any questions from the audience? Please.
So okay. So this is sort of my disclaimer. We didn't look at incentives at all, even from the theory perspective. We sort of looked at the agents, or the software agents, that we can program multiple things to operate together. The agenda would be first to try to define rational agents with complete rationality and see what we can gain. And then comes the issue sort of how much people will really cooperate, or sort of how much people will follow the recommendation as given. This is another layer of definite complication.
Any other questions? Yes, sir.
For the
Can you repeat the question, please?
A use cases that you can think about. So towards the delay, I gave you sort of multiple things. I think sort of essentially think about users giving a recommendation or given, let's say, stars, I don't know, in Amazon or in your favorite online store, right? Those are way of cooperation. Sort of essentially through their reviews, they are sort of providing feedback about the product, and those are sort of shared for in some sense, the other user will select the best product, let's say.
Just next to.
Okay.
Oh, yeah, you were there first.
Okay, yeah, so the model that I described was a multi-arm bandit called. So a multi-arm bandit is a setting in which you have just a single state, unlike a Markov decision process, and sort of the way that I would, so in some of the solution, the agents are not homogeneous. The one that I mentioned with sort of the clusters and the red point, there is sort of a leader, there are followers that are connected to the leaders, and the rest are just sort of receiving from the leader a distribution over the action, what they should be doing. So the question is, can we generalize it to the continuous case? You mean continuous time? I think what we've been mainly working on in sort of in these long references was to generalize it from a single state, multi-arm bandit, to a Markov decision process where there are multiple states. For continuous action, we'll need a model for the continuous action that would make sense, but I think sort of things will carry over there more naturally. You would like that to define that similar actions will get similar rewards, right? Leaf sheets, if you are familiar with the term. So under this, I would expect that you will be able to generalize.
Thank you. Thank you very much.
Thank you.